Morning, everyone. How are you? All right. So the plan is to keep you awake for 30 minutes, because after that I don't care. Then it's on Dave Pearson after that, and then Tim. So welcome this morning. Thank you for the introductions, Mbali. We're going to give you an overview, really, of the non-revenue water strategies. And it is really intended for novice, but I think very quickly we'll be delving into some details that I think there'll be some takeaways for everybody here today. Tips that I think we've put together in the various strategies that even if you've been in the business for a while, I think you'll have some value that will come out of our sessions this morning. So there's no better way to start things than really to talk about leakage. I mean, what are we talking about here? Pipes and types of leaks and types of flows and so forth. So we thought we'd just kind of set the stage here to talk about what the issue is, what some of the things that the guys will talk about in terms of pressure management and leakage a little bit later, in terms of DMAs and how to find these things. And so let's get cracking. I'll give you an overview of leakage, understanding of leakage. But first, we can talk about leakage or we can talk about fishing. Some of us like to fish. Like Mr. Tim, he catches fish. This is a big one. Now, Tim, of course, will tell you he catches bigger fish. No, he took me, he came down to Niagara region, and we went out fishing in Lake Ontario, and I caught a fish with Tim. Now, the thing about Tim's fish over there is that he sent me that after I caught that fish. Picture Tim, it's bigger. I've got a bigger fish there. But he was talking about the one that got away. They were in the boat. Tim had one on the line there for about a half an hour, and you could hear the thing going. And Tim says the fish has got to be at least that big. Of course, he couldn't reel it in, but I reeled mine in, and that's okay. But Tim had to follow it up with a picture about a month later of his fish, which was bigger than my fish, which is really what it's all about in terms of fishing. Now, our colleague here, Dave, he doesn't fish. He thinks about fish, but he prefers to eat the fish. So his claim to fame is, I don't care what you guys do with it, as long as you can dish it up, I'll eat it. So on the right there, that's his idea of fishing, and that's our collective idea of fishing. And I could go on about fishing, but I think we'll kind of carry on to really what we're here to talk about, and that's leakage. And the problem is worldwide. Leakage is happening everywhere, every country. Developing countries, first world countries. I wish I had a nickel for everybody that told me all of our leaks come to the surface. We don't have a leakage problem. And that's part of the problem, that we don't recognize the extent of leakage. David's probably going to talk about a water balance and talk about how to assess the amount of water that's lost. But really, we, as an industry, and I'm a utility guy, we're all utility guys. We're doing consulting now because we've retired. We can't stay away from this stuff. We're just passionate about leakage and loss control and just can't get away from it. It's in our blood. But we're utility guys. And as a utility, we really haven't done a very good job, to be honest with you, our industry. I can't say I'm particularly proud with the job that we've done recognizing the problems that we have in our own operations, recognizing the level of leakage, the level of losses, and a sense of urgency that needs to come to bear to address the problem. It's a failing that we have. And I think only through talking the truth about how much water we're losing and what you need to do to address it, to move you from where you are to where you should go after you do an analysis, I think is, particularly in these, with climate change and going on, and particularly what's happening here in Cape Town, really brings it home for me and for us, the severity of the problem, not only from leakage, but from climate control and source management. It just makes what we're talking about here all that more important. So the problem really is that water leakage is on the rise everywhere. And whether it's our systems, particularly for metal, that are deteriorating, it's a problem inside and outside the pipe. It's corrosion issues, it's poor quality in piping and connections, where most of the leakage occurs. It's past installation quality or lack of it, how it goes in the ground, proper bedding, proper construction techniques, and the absence of active leak detection program. The leaks tend to run a lot longer, and you're going to hear that theme throughout today It's really about leakage runtime as we deal with leakage. And in as much as a lot of this is relevant to metal pipe, we still have many of the same issues with plastic pipe. And worldwide, there's more plastic, elastic, plastic, polyethylene pipes going in the ground, which presents, certainly from a leakage control perspective, more challenges because it doesn't transmit leak noise very far. Some would argue I don't think it goes very far at all. Not predictably well. You might get lucky and be able to acoustically find leaks on plastic or elastic pipe, but not with certainty and not every time. So some of the techniques and strategies we'll talk about a little bit later through DMAs and step testing are additional tools that we can bring to bear to deal with mixed pipe considerations, which is a real issue. Mixed piping and control of the data and so on. And then there's pressures and significant variations in pressures. Pressures are an issue. It's a challenge. Everyone likes to have big pressure to operate washing machines and take a nice shower and those types of things. But pressure is a problem, and we're going to delve into that, I think, quite deeply here this afternoon about effects of pressure and variations in pressure as it relates to, I don't want to steal any of your thunder, Dave, no? I'll stop now. So we'll carry on. So types of pipes. So, no, I know. It's just, we'll just more time to have coffee or go talk fishing a little bit later. Lots of different types of pipes. All right, so we've got metallic pipes, we've got cast iron and ductile iron, and where I come from, 40 to 60 or 60 to 70% of the piping systems are metal in North America. And now most of the new stuff going in is PVC, so we're seeing a higher percentage overall in the system moving towards plastic or elastic pipes. Europe and the UK, I think you have probably a higher percentage of plastics. And certainly it's a much cheaper product to purchase, so there's a lot more of it going in the ground, which will present more difficulties as we move on in the future. But beauty of metallic pipes that transmit leak noises very well when we get into leak detection. I'm going to talk about that a little bit later here today. Asbestos cement, there's a fair amount of that, as I understand, in South Africa. There's a high percentage of asbestos cement AC pipe. And the beauty of that stuff is that if there is a leak on it, you can hear it. And that's a positive in a sense. That's about the only positive I can think of AC pipe, but in any event. And then there's various numbers of plastic pipes, whether it's PVC, polyethylene, polypipes, plastic pipes, various grades and qualities, and some of them are not very good, which again brings us back to the number of leaks that happen on connections and services. Then there's reinforced concrete cylinder pipe, and the classic that you can see on the picture there is spiral reinforced wooden pipes, which are still in service in some areas that are well over 100 years old. And this is in our home province where I come from. That's one of the transmission mains that's still in service. Well, let's talk a little bit about when a leak occurs. So that's a type of pipes. Leaks occur in pipes. Different types of pipes have different types of leaks. But typically, when a leak occurs, there's noise generated from the escape of pressurized water through a small fracture or orifice. The tighter that crack or orifice is, kind of the higher intensity that happens, creating cavitation effects. There's noise and vibrations are generated. A metallic pipe, that will transmit down the pipe wall, and you can hear it upwards of several hundred meters in either direction. And a plastic pipe, because it's elastic in nature, it doesn't transmit very far. Sometimes a couple of meters, 10, 20, 30 meters, but not much more than that. And the more plastic you've got in, it just tends to absorb those vibrations, and you're limited in the propagation of that leak noise down the pipe. So if you have a leak that's occurred here, as an example, the leak noise is transmitted along the pipe wall to the extent that it will transmit in plastic, and will go quite far on metallic pipe. Not quite so far in asbestos cement pipe, but it travels through the pipe wall, but also transmits through the fluid as well. So there are some tools that are out there that you can, different types of transducers that will pick up the sound of the leak through the water medium. A lot of people don't use those techniques because it's very labor intensive, but the fact of the matter is there are techniques that you can pick up the sound of a leak transmitting through the water. And then there's the noise that are generated around the leak itself from the water escaping, hitting the surrounding soil. So there's kind of three areas where the leak noise gets transmitted: through the water, through the pipe material, and in the surrounding area there, where that leak noise tends to transmit up, and if you're doing acoustic, leak detection, you're listening for the loudest point of sound on the road above where the leak is. The problem is you need to bracket where the leak area is. There's no sense in doing detailed work all over the place where there are no leaks. You should be focusing your attention where the leaks are, or a higher probability of where the leaks are. So you can do the detailed leak detection and pinpointing where there's a higher probability of being successful. That's a theme I'll come back to a little bit later. But generally, that's really what we're talking about. So we have different types of pipes, different types of transmission of leak noise through the water, through the pipe, and in the surrounding area, and various number of pieces of equipment that I'll talk about a little bit later as well. So there's all kinds of different leaks. You've got circumferential breaks, you've got small splits, you've got explosion and explosion. Pre-stressed concrete cylinder pipe, when it fails big time. When PVC fails on the bottom left, tends to have a spiral split. If there's sufficient pressure, it will simply explode. Now, these will be surfacing leaks. They won't be very hard to find because both of these leaks at the bottom took out several hundred meters of road. It just goes with high pressure. The other ones, these didn't surface, and they can run for a long time. And my argument will be some of them have been running for years. Very high flow rates, very high volumes of water that are lost. So let's talk a little bit about the types of leaks and losses. Well, splits will have very large volumes of water. Usually they will come up simply because it just floats, it just blows up. The volume of water will just float all of the covering material away. So depending upon the size of the pipe, the split length, and the pressure, this will all be relevant to the amount of leakage flow rate and overall the volume of water that will be lost. Main breaks tend to have larger flow rates. So on metal pipe or AC pipe, most of the time you have a circumferential break, and depending upon the pressure and how long it's run and how open the fissure is, you can have a significant amount of water loss by way of flow rate as well as overall volume. I'll talk about that in a moment. Service line leaks tend to have smaller flow rates, but the counterpoint of that, they tend to run a long time. So the volume of water loss tends to be quite large. That's a theme that you'll hear a little bit later this morning. You have leaks on joints and fittings and couplings, depending upon how much they're leaking and the size of the joint, the size of the fracture, and so on. It could be small weeps to large leaks. Fire hydrants, those types of leaks that have steats tend to have a smaller volume of water. Corrosion of metal pipes, pinholes, and cracks, it's variable depending upon the size of the orifice, the amount of pressure, number of pinholes. You can start ramping up in terms of a reasonable amount of flow rate that's there. And then there's other hole splits and circumferential breaks and so on. So we've got small leaks on fittings, small leaks on small pipes, small leaks on big pipes, big leaks on small pipes, and you know, that's how she goes. I'll have a look here in a moment. But so when we're talking about leakage and losses, we've got the different types of pipes, we've got the different types of leaks, and all of them will have almost a different, if you will, flow rate that would be associated with them. So my experience, having been doing DMAs for quite a while, these are generalizations. Let me just say that right off the bat. But typically, you will have a typical flow rate for a typical type of leak that's there. These are my numbers. Everyone will have their own number. It's really, I'm just talking about an order of magnitude here. I've done acoustic leak detection for over 40 years. I started when I was at university, and by the time I left, I had bought my own equipment, and we were doing surveys before I was a professional engineer. And I've used every piece of equipment on the market. And I'm still doing it. I did a survey last year, so I'm still beating the roads on this stuff to keep the, you know, if you will, keep the saw sharp, to keep close to the action. My view is you can get a threshold of detection repeatedly down to these levels of about less than a liter a minute. You could argue maybe down to half a liter a minute. It depends on type of bury, depth of bury, amount of pressure, and so on. But there's limits to what you can find acoustically. And with noise correlators, there's limits, depending upon the setup, the amount of background noise, variety of different things. If you get at the different types of leaks, from service leaks, from 19 millimeter as you move up, the corresponding general flow rates for a typical leak is in these orders of magnitude. whether it's going from 0.2 or 1 liter per minute to 14 liters per minute for a 3/4 inch, or 19 millimeter and so on. So I won't read this off to you, but typically for larger distribution systems in North America, because we have a higher frequency of mains breaks than we do services, in my experience. And in Europe and many other countries, they have a higher frequency of service and fitting leaks than perhaps main breaks. Now, if you start associating the numbers or frequency of the leaks in your system, start thinking about the flow rates that are there and the types of leaks that you have and how long they run, and you start to get a good idea around what your potential problem is. And then we're going to talk about the strategies of how to go and find those types of leaks. But each system is different. Pressure, number of connections, what your break frequencies are in your system based on the type of material that you have, the sizes of your mains, whether there's fire protection or larger pipes or smaller distribution pipes. But this just gives you a spectrum. And then when you get up into the splits, well, you know, we're talking just, you know, it's off the Richter scale. 10,000, 20,000 gallons a minute is not uncommon. When you get into large splits, they will show up because there's just the volume of water is overwhelming. But again, depending upon the size of the main and how long the split goes, it goes vertical in terms of the volume of water. But this gives you a sense, just put things in perspective about sizes of pipes and the types of volumes or flow rates that you can get from it. And at the end of the day, this really is about the volume of water that's lost. We talk about leaks and flow rates, but it's, at the end of the day, it's about the volume. And the volume is the flow rate times the run time, right? That's the key. We're going to spend some time on that one today, about run time. But this gives you a sense of the flow rates, and then it's the run time. And then we're talking about really the volume of water that's lost. Now, at the end of the day, you can also say, well, that volume has a value. So this is where your business case can be developed to make investments in water loss because you have a payback. So the volume times the cost of your water, the marginal cost of your water will give you that value. And you know what? The business case on this stuff is very simple. The paybacks are there, and it makes your job as a utility manager quite easy if you can build a business case predicting how much water is lost, its value, and making investments in technology, people, resources to address the problem. So then, so let's move on. There's reported leaks and unreported leaks. Well, here's a reported leak. There's a no-brainer. It's blowing the road and away she goes, and obviously very high pressure. Reported leaks are the ones that are called in by the public. They're surfacing leaks. You can see them. Someone calls up, we've got a problem, so you're immediately aware of it. Immediately aware of it. Then the question becomes, how long is it going to take for you to get out there and either turn it down or get it fixed? Usually, in most utilities, this is within several hours. Unreported breaks are non-servicing breaks. It's the ones that you don't see. They're not visible, and the utility may be unaware of the leak occurrence for an extended period of time. And in the absence of DMAs, which my colleagues will talk about here, you may not know how many that you have or how long they're running. This will contribute to the backlog of leaks that you've got in your system. I'm going to talk about that a little bit later. You've got active leaks that come up that you address right away, and then there's a backlog of leaks that are probably the sum of which are killing you in terms of your overall leakage problem. You've been running a long time. You don't know where they are. You don't know how many you have, so you don't know how to tackle the problem. So you may go out and do a survey and just like a shot in the dark, and you come back with mixed results. And 6 months later, you're right back where you started. It's deja vu all over again, and I've seen this over and over again in systems around the world. You're on a cycle of find, fix, repair, and you just can't get ahead of it. So if you break it down and think about that backlog of leaks, you've got to get the backlog addressed. That's one type of activity. And then deal with new leaks as they come on and set up processes to deal with that. So I want you to perk on that one for a minute, and then we'll kind of move on here. Unreported leaks require active leak detection to locate. DMAs and step testing will give you the area where it's in and maybe the flow rate that's there, but you'll have to require some active leak detection to find it. I just mentioned here a moment ago the water leakage backlog is typically high in high loss systems. There's a lot of it. If you don't do a proper water balance, you really haven't define how much is in there. And that's why that's so important in the fundamentals of getting a standard water balance to determine the amount of real losses in your system. It's an accumulation of unreported leaks that have not been located over time, days, months, or years. Years of running at high flow rates. So the simple math on it, if you look at the years, that's 1,440 minutes a day times 365 times 100 gallons a minute is a big number for one leak. Systems that have high losses have hundreds of leaks. They're running 7 days a week, 24 hours a day. That's the killer. Right, tip of the day, in chlorinated systems, black gravel indicates a long leakage runtime. This is my experience of digging thousands of leaks. What does that look like? In this case here, Mr. Yates, you'll notice this one. This comes out of your backyard. See the black gravel down by the bottom of the pipe? And in this case here, and in this case here, there's black gravel indicating there's been some leak has been going for an extended period of time. In this case here, there was an explosion here, but there was some weepage that was going on a long time. If you come across and you've got gravel bedding in a chlorinated system and you see black gravel, my estimate is it's been running for years. Just a tip. It's an indication of what you've got. If you don't dig a lot of leaks, you'll never see it. You won't see it. But I'm just drawing your attention to that. That's the tip of the day. Various leaks have different noise signatures. Each type of leaks has a different sonic signature. Noise intensity will increase with pressure. The higher the pressure, the more noise is generated because the cavitation effects are larger. It generates more energy, more noise, and if it's on metal pipe, it'll be transmitted over a longer distance. How far? Hundreds of meters in either direction on a metallic piping system. Hundreds of meters in both directions. They had some jazz on a little bit earlier that I really enjoyed. You missed my little jig when I was up here. Large and small leaks may generate loud noises and log propagation on metal pipes. That was funny. Sorry about that. That's usually my pick up the bread and milk kind of call that comes in when you're in a presentation. You know, don't forget when you're coming home. The noise intensity may vary widely with the size of leaks. Sometimes small leaks will generate a big noise. Sometimes big leaks will generate a small noise. Sometimes big leaks will generate almost no noise. It's a bit of an oxymoron. Leak frequencies or pitch will vary with the orifice size and the tightness of the fracture. The tighter it is, the higher pitch it is, sometimes the louder it is. As that fissure opens up a little bit more, the pitch goes down, less cavitation effects, more lower frequency, more of a roar. That's why the mains breaks have a deeper sound to it. So it's pressure, size of orifice, cavitation, all have an effect on the pitch of the noise that you'll hear. Narrower the fracture, the higher the pitch, the larger the discharge path, the lower the frequency, in my experience. So real loss rates, well, if you look at the annual volume of real losses, everyone has a certain amount. You can't get it all. But there's always be a volume that's there. And if you're unable to get the leaks when they occur and you get the backlog of leaks, every year there are more rebreaks. And if you're doing budgeting, every year you budget about the same amount of budget for break repair because there's about the same amount of leaks occur every year. But if you don't find them all, they go into the backlog of leaks that you've got, and then, they accumulate over time. So year after year after year, if you don't get the backlog of leaks, what you end up with is a lot of leakage. It's a backlog of leaks that you've got with high losses for your utility. You gotta deal with the backlog of leaks as one strategy, and then deal with the new ones as they occur as a different strategy. You can use some of the same strategies in toolbox the boys will talk about here, same tools. But to think about it in a different way, it breaks the problem down, in my view. System breakage leaks for good conditions. I'm going to give you some background here. How am I doing for time in Valley? I'm going to run out of time. I'm in 8. I can't do it in 8 minutes. Main leaks. So this is interesting stuff. Usually, this came out of the UK. But main leaks in Europe and the UK experience, typically for systems in good condition, you get 13 to 15 leaks per 100 kilometers per year. for main breaks, of which 95% are reported and 5% are unreported. This is what I've got from Alan. More or less. I don't know. Run with me on this one, and then we'll come back. And this was predicated when all this kind of came out, based on a lot of the information that came out of Germany, the Netherlands, France, the UK, some of the American data. Approximately 36,000 kilometers were assessed to come up with some of these average leak frequencies. Really doesn't matter too much. We're just giving you context here of where the 13 to 15 leaks came from. The service leaks connection in Europe for systems in good condition. Typically 5 leaks per 1,000 connections per year, including the public and private side. What we mean by that is, depends upon where the water meter is. If it's located at the property line, that would be referred to as the public side. If it's in the home, you'll have typically a different section of the service line that's pressurized, where the water leaking would not be metered. So that would typically be on the private property side of the service shutoff at the property line. The combination of those two, approximately 5 leaks per 1,000 connections per year, the ratio being 3 on the public side, there's more connections on the public side, and 2 on the private side. Just an apportionment of where typically the leaks would be. And 90% are reported and 10% are unreported. Just as another tip, this came again from Alan, service leak rise time to go to full flow rate from when this small leak starts till it gets a full flow rates are typically in the area of about 2 years from going from a small leak to moving through. So there's a period of time where they'll get worse until they top out in terms of a flow rate. North American perspective, the purpose of this is to put things in your perspective, okay? Think about the types of leaks that you have in your system, how many you've got, so you can have some relationship to what's happening, because systems are different in different parts of the world. Okay, the way they're designed, as I mentioned that earlier. North American systems have larger distribution mains and smaller pipes than in Europe. And typically there's more main breaks than 15 per 1,000. In fact, we're seeing 18 to 31 main breaks per 100 kilometers for systems in average condition, not particularly good condition, or higher. It's almost twice as many as the European experience. 75% because of the types of soil and depth of bury that you have. If you've got frost conditions, you're going to be down 1.5 to 2 meters, sometimes 3 meters deep. So leaks don't tend to surface as much. So you have a higher percentage of surfaces or breaks that are non-reported. They're not coming up. And in Halifax, in my experience, over 75% are unreported main breaks. They don't come up. Older systems will have, that are leaking more, have a higher frequency of main breaks per 100 kilometers. And service leaks are less than 5 leaks per 1,000. In fact, I'm seeing data that I've looked at through Canada and the US that are down in the order of 1 to 2 service connection leaks per 1,000 connections, about half. So North Americans, just rules of thumb, about twice as many main breaks as the UK European experience, and about half as many of the service leaks. Why? The systems are different. You have larger main breaks, or higher lengths of larger mains, and not as many lengths of mains of smaller pipe. So more main breaks on than Europe, and less service leaks. Always exceptions to the rule, but again, my experience, and 90% are unreported. So most of them don't come up. So the leak runtime runs longer. Unavoidable water loss. I'm going to skip through this I got 2 minutes. I'm going to skip through this because David is going to talk about this. Aren't you, Dave? Yeah, main leakage. This is just giving you some background, minimum levels of loss on background on main breaks and service leaks. David, you going to talk about that? Yeah. Good. I'm going to move on. Unavoidable real loss calculate. It's a plug and play. You can calculate the minimum levels of losses in your system by putting information and putting it in there to come up with how low can you go. David's going to talk about that. And what the unavoidable levels are. That's the minimum, that's a little bit of the weepage that takes place, plus minimum leakage runtime is embedded in that formula. David's going to blow you away with the details on this stuff on his presentation, I can guarantee you that. You'll be hanging by your thumbs while you're looking at that. Background losses. BABE concept, this is just background losses, break estimates. David's going to talk about that. I know he is. High leakage systems, moving to the fun stuff. My experience when I was working in Halifax, we started to kind of look at data and leak clusters. They have different color codes up there, but in 2001, these are main breaks that were repaired in an area mostly of metal pipe. And what you'll find here, interesting, is that in the circles, there's more than one repair per year. Multiple leaks. In fact, most of the leaks in an area, there was more than one leak that happened over the year. And if you look at it, there's clusters, and this was a fairly high leaking system. Let me just say that. For high losses, there's multiple leaks that will be. And from year to year, we had a look the next year and look at the different 2002, look at the clusters. You go from 1 leak, 2 leaks, 3 leaks, 4 leaks, 5 leaks in a certain area. Remember I talked about the leak? If you have a leak noise, it'll propagate 300 meters in another direction. Those circles in through there, if you had a leak, influenced all of that area that's there. So I'm saying, if you go in and you find a leak in an area that has high leakage and you find one leak, don't go home. Because there's probability of more leaks in there around the corner. How many more? 50% of these things have got 3 or 4 leaks. 70% have more than one leak. In systems of high leakage, there's multiple leaks in it. Watch me go, and Bella, I'm gonna roll along. Ottawa, before any leaks were done, look at the amount of potential leaks that are in these areas here. We just listened to the noise and mapped the noise out, the probability of leaks. So we want to focus our attention where the leaks are and not where they're not. So by doing good leak detection, you can dismiss areas that are in the green. This was all done electronically and posted on a GIS system. This is a noise map of color. This noise, the colors depict noise. So you see the higher concentrations of noise that are there indicating multiple leaks before we dug anything. Before we operated any valves, we see multiple leak probabilities that are there. 60% of those were leaks. 40% were not. Consumption or something else that was there. So very quickly, this is one system with 3 years of data input going from January to December. That's 1 year. This is a system that has virtually no leakage. And in this area, in Canada, we've got severe leakage. It occurs in the winter, but it also has the least amount of water use, outdoor water use. It's the lowest amount in the winter. So you'd expect the lowest flows coming from the treatment plant should be in the winter. And that's what this shows you here. Those are excellent results. That's summer consumption. June, July, August, September. Summer consumption, we sold all of that. And then the flows returned back to low levels. Here's an area of another system for 3 years, inputting this area here from January to April is higher losses. We had this leakage that was occurring with longer leakage runtime because of winter, right? Year in and year out, 3 years running, you know, as much as there's been a little bit of reduction there, you see the longer leakage runtime contributing to higher losses. All right, so you need to develop a strategy around that if you want to deal with this problem to bring you back to the first situation I showed you. So impacting dealing of losses, I'm going to go right along here. Reducing losses has operational effects. What does success look like if we reduce losses? Stuff happens. If you reduce all of that flow and volume of water out of the system, something's got to happen. What happens? Large reductions will generate higher pressure, will generate more leaks. And this will get you on a turn cycle. Dave's going to talk about that in terms of pressure management. You fix leaks, the pressures go up at night because the flows aren't there. Be aware and monitor increased pressures in your sector. High pressure increases flow rates. If you reduce some leakage, the pressure goes up, you leak more. Reservoirs will fill faster with lower losses. You have to change your standard operating practices for your reservoirs because you got more water availability. You can fill your reservoirs faster. How does that impact your water treatment plant? You just can't operate the same way. If you strip out 30 or 40% of the water you produce, you have to change how you operate. Operations, water treatment plant, and pumping may be affected. Expect changes in your system performance with lower losses, hydraulically, from a water quality perspective, and from your pressures. There's consequences for lowering losses, but this is what success looks like. If you're successful in reducing big leakage, this is what's going to happen. So you should be prepared for it. Otherwise, you'll find yourself on the treadmill of find, fix, or repair, and you won't be able to get out of the cycle. This is the management part. I'm going to stick management here for a minute because the management, it's just not all about operations. Now, I've managed 3 water utilities in several provinces. Systems that have high leakage, management doesn't believe there's a leakage problem. You got to put it in their face. You got to do a standard water balance. You talk about the value of the water that's lost to get their attention. There's no sense of urgency to set up a strategic or work plan based upon your problem. We got a leakage problem, but nothing happens. It's not resourced. It's a management problem. Lack of leadership, no champions to engage staff. It's a management leadership problem, along with an operations resource. Poor communication of leak awareness. This is huge. Slow information dissemination of when, where, the volume, and flow rates are occurring to get out the leak crews. Disjointed, fractured departments, someone else's responsibility, non-responsive. It's a management problem. You got to fix that. No scheduled meetings to review leak process, leak rates, or reallocation of losses, and poor tracking of system inputted leaks. It's a management problem. Can't stick this to staff. This is not a staff issue. It's a leadership issue. Lack of delegated authority for staff. I've seen this. Authority and responsibility don't line up. Someone else is responsible, but I'm accountable. Well, how can I manage if you don't give me the responsibility to manage the resources? It's fractured. It's disjointed. It's got to be aligned. Poor management alignment, fractured department, no changes in standard operating procedures, lack of training and resources. It's a management problem that's here. So as much as we're going to talk about strategies, if you don't get this done, you're doomed for failure. It's not sustainable. And with that, losses speaks volumes. Sorry I'm late, my dear. All right? So I'll turn that over.